Good afternoon, fellow foundrymen. This is Sandil Kumar, Secretary from IIF Chennai chapter. Before we get started, I request everyone to put your mobile phone in silent or in vibration mode so that it's not disturbing the presentation. And all your queries, you can raise it at the end of the session. Either you can through your chat, or you can you can ask online. Okay, it gives me immense pleasure to interacting with you for yet another webinar, which is being conducted by Indian Institute of Foundrymen Chennai chapter jointly with Southern Region. To get things started, now I request Mr. Sanjit Kittur, IIF Southern Region Chairman, to welcome the gathering, please. Yeah, Sanjit Kittur, sir, please.
Yeah, thank you, Senthil. Am I audible?
Sir. Yeah, you are audible, sir.
Yeah, good afternoon, gentlemen. I take this, it's my privilege and honor to welcome you all for the webinar, which has been conducted by IIF Southern Region and Chennai chapter on the topic Gating and Risering for Steel Castings. I also welcome today's speaker, Mr. K Manogar, Consultant, Lakshmi Ring Travellers Coimbatore. I think it's a beautiful topic that Chennai chapter and Southern Region have chosen. I request everybody to hear out the seminar properly, and so that you can have a proper knowledge in today's topic. So that's it, gentlemen. Thank you for being here. Thank you.
Thank you, sir. Now I request Mr. V.K. Raman, our Chennai chapter chairman, to introduce the speaker to the audience, please.
Yeah, thank you, Senthil. Am I audible?
Thank you, sir. Yeah, you are audible, sir.
Yes, sir. Good afternoon, Manogar, sir. This is Raman.
Yes, sir. Good afternoon.
Sir, thank you very much for accepting for this webinar, and I am very privileged to introduce you for the fellow foundrymen. So Manogar, sir, is having he is running a own pattern shop and aluminum sand casting business for the past 2 years. He widely traveled in India and visited many major foundries, ductile, steel, aluminum, and the forging shops. So his development of casting varies from 1 metric ton to 300 metric ton for various parts of ductile. Steel castings weight ranges from 100 grams to 1500 kg in various rings, and 500 parts in investment casting processes. Further developed forgings from 2 kg to 60 kg for many parts like axle shaft, pinion, etc. The consulting services on development and inspection services for aluminum, GDC, PDC, plastic parts, pattern, castings, etc. On education part, he initially completed diploma in mechanical engineering in the year of 1976 at Chennai, and gradually improved his academic part by having industrial engineering graduation, PG diploma in total quality management, and various diploma in management, marketing management, and completed PG diploma in metallurgy in CPT Chennai. And he is also a certified green belt in Six Sigma methodology in Caterpillar, India, and a certificate course in marketing management in the Academy of Career Guidance in Delhi. Knowledge on 3D modeling using Unigraphics, NS6, use of simulation software for Risering. So on education part, he covered all the areas, nothing is left. Worked in many companies, starting from Sivananda Steels to various companies, Caterpillar India, then Hindustan Motors, then Was Industries Private Limited, and many higher position held in these various companies. So, highly knowledgeable man having widespread experience in the field of foundry is going to present us the topic on risering of the steel castings. I request to all the fellow foundrymen to attend the program fully, and any questions can be raised at the end of the program. Now I request Mr. Senthil to proceed the program further. Over to Senthil. Thank you.
Thank you, sir. Thank you very much. Small announcement for again, gentlemen. I may request you to put your even camera switched off, so that we can give proper attention to the speaker. Manogar sir, you can start. Please start your presentation. Forum is yours. Thank you.
Thank you. Thank you.
Thank you, sir. You are audible. Yeah.
Yeah. You are able to see the screen?
Yeah. You can go to the presentation mode, sir.
Yes, presentation mode only it is there.
Yeah. No, it is not in presentation mode, sir. Just go to slideshow. Okay. Just go to slideshow. Yeah.
Yes,
yeah.
Right.
Right.
Okay.
Yeah. Now it's okay. Fine.
Okay. Yeah. Good afternoon, Manogar from Chennai. So I'm thankful to the IIF Chennai chapter and Senthil and Palani Murugan, Dinesh, everybody for organizing this. And I'm privileged and thanked for IIF chapter, Chennai chapter. They organized the same getting and raising class which I attended in 1985, if I'm wrong, if I'm not wrong. So the same thing I'm going to present with the additional information. Okay. The topic is for principles of getting and rising. All institutions and scientists who contribute to the foundry industry, the fellow foundrymen from whom I gather knowledge either directly or indirectly. I just compiled various information and experience which I acquired during my service in various foundries and foundries visited during my development of castings for my previous employers. And rising only we are going to discuss, assuming that all the participants are all the foundry processes. This is only basic working up how to do methoding, and this will be mainly on methoding only. Present for the small and medium foundries, not for SG or grey investment castings. But some principles we can use. All the information are shared in that. So why getting and rising? Customers need sound casting. So what's the sound casting? As per Steel Foundry Society of America, it is class 1 soundness at 2% radiographic sensitivity. Olden days we used to say it's a sound based on the ringing sound. So we call it sound casting. Nowadays castings are accepted based on NDT results like radiography, ultrasonic, and some of the cases are accepted only after machining if there is no defect or leak test. Even some of the castings for food processing, you do polishing, and after polishing there should not be any black dot or small dots are not accepted. Visual inspection. Other NDT like BP, MP also is being used. UT. What are unsound casting? The presence of following defects beyond specified or agreed quality levels based on its application and functional requirement. This is shrinkage, crack, arc tear, inclusion, slag, oxides, gas-related defects, rough surface, flow lines, leak while hydraulic testing, any defect open on machine surfaces. How to achieve sound casting? It is based on technical and economic considerations and planning right from design stage, casting process, volume, application, and ease in manufacture. That is one, a component design and process design. The component design, we as a foundryman, we have to work with our customers so that we can explain our difficulties, get the design made such a way that it is make easy for us to produce. So as a part of designers, they also nowadays do all this 3D modeling and simulation, and they ensure that their design is foundry friendly. In case some of the old part numbers or some customers, they're sending drawing, we find it's difficult for producing casting, you can always talk to them, make them to understand our difficulties and get the design change. And foundry should always aware of the customer and products, application of the casting which will avoid unsuitable development. Ask for the requirements and spell out the quality that you can supply at the beginning itself. So process design involves the following steps: designing of getting and rising based on required quality levels, pattern design that includes parting line, loose piece, core or self core, and what is the number of cavities based on the quantity, and pattern and core box materials depending upon the process. Mold and core process, melting and ladle and pouring practices, cooling time of poured molds and knockout methods, cleaning and filtering, heat treatment, weld repair process. Inspection methods of both incoming middle and finished casting, process control and auditing of internal soundness, that is sample size, sequence, first mold or last mold, sampling and frequency, once in a year, every day or every month. What is the frequency depending on your quantity? Designing or getting a risering based on record quality level. This will be discussed in detail. What the other steps in this process are pattern design, planning and right tooling make the good casting, estimate the risering and getting first before you are designing the pattern design, so that you know where the exact part line, how much print you have to give, where the core locks to be given, or any other gauges, core setting fixers, templates required for the component to come out all right. What happened? Foundries make patterns from outside, or they use the custom submitted patterns, but then rely on the pattern maker for inspection report. But as a foundry, we should inspect the pattern ourselves, so that the methoding person knows what are the dimensions in the pattern, which he can use it for risering purpose. Without inspecting, then we are going as per customer pattern, then we will be in trouble, because the pattern may not be suitable to the individual foundry conditions. Mold and core process. There are different processes, so we have to select the different process for a particular component, or a combination of the process for a given component. For example, where you can use a CO2 core may not be okay, you have to go for a shell core. And again, based on the process, what you are going to decide, the contraction will vary. So for example, CO2 process means for a core it was 1.3%. When we change the process to no bake, it was contracting 1.6. Then we will be landing into dimension problem. Melting and pouring, this we have to go through other details. Cleaning process. So not only shard bashing is sufficient, sometimes we have to do other fettling or machining. Sir? And speed or slow?
Hello.
Inspection of knockout.
Sir, voice is breaking, sir.
No, somebody was interrupted, so I thought I stopped. Okay.
Okay, right.
Okay, now?
Now it's okay, sir. Please.
Casting will tell the equipment condition, setting, sitting, mold bend or gap at parting line, mold core quality, defects due to gating, risering and pouring practice, still marking errors or cutting errors, like that. So scientific of designing the gating and risering will result quality casing, either manual or use computer simulation will help to optimize the rising. Why gating and rising? To achieve sound casting, properly designed gating and rising is required. Apart from other parameters are taken care. We often see foundries have all kind of facilities, techniques and technology, but lack in methoding. Companies investing in all that, but there is no proper person to do methoding. So methoding decide the profitability of the foundry. If you overrise, then it is less productivity, loss of metal, melting, cutting, everything. So it is a good to have a proper methoding person. What is a finishing and risering? Feeders also known as riser. Risers added reservoir designed to feed liquid metal to the solidifying casting to compensate the liquid and solidification shrinkage. Various risering designs. This one shape factor method, which are all not used nowadays. Geometric method, Weaver's interrupt circle method. This somebody is using for a shortcut. The scientific way, or the most of the principle of what we use in steel foundries is the modulus method or load-over. As per Koravanov, that solidifying layer obeys the rule x equal to k square root of t, where k is a constant depending upon the boundary conditions. Modulus is the ratio of volume and surface cooling area. Then only the freezing ratio. Next one, freezing ratio is the ratio of modulus of riser and casting. This concept was developed by Mr. Lodover for practical riser calculation by eliminating the need to calculate actual solidification times. In the radar system, the feeder I did recommend is deduce from the cooling modulus. The casting being subdivided wherever necessary into basic shapes, for each of which the volume area ratio can be readily determined. Only the cooling surface are included in the calculation, the imaginary contact surface being omitted. The feeder is then selected on the principle that it should have a modulus value 1.2 times the casting modulus. This will be discussed in detail. Factors in feeding, three principles. One, freezing time. The freezing time of riser and casting are proportional to their respective modulus. If the modulus of riser is sufficiently greater than the modulus of the casting, good feeding will be obtained. Feed volume. The volumetric shrinkage of casting should be fed by the riser. The riser should be capable of supplying the sufficient volume of liquid metal to compensate the liquid and solidification shrinkage of the region where the riser is connected. Volumetric shrinkage of varies for different metals, which is shown in the table. You can see there. Feeding range, which is concerned feeding distance and feeding length. As per Steel Funds Association, feeding length, this is the theoretical feed length of the casting or section under consideration to be fed. The distance from the riser to the farthest point is the casting, it is the length to be fed. It is purely geometric value. Feeding distance, this is the distance. Feeding region is the area of the casting which will fed by a single riser. Feeding areas which are bounded by end zones are larger than those without end zones. Steps and method are study the drawing and mark junctions, AB sections, need feeding are identified through simulation software. Calculating the modulus of the selected section, find the riser number. Calculate the feeding range, feeding length and feeding distance based on the casting thickness. Decide whether top or side riser. Calculate the neck dimensions and foot up if it is side riser. And riser should be capable of feeding the foot up weight also. Calculate the feed volume or the weight of the selected section, making on drawing for feeding regions and confirm all the areas are covered in case of bigger castings. Preferably do it on actual pattern. Once the pattern is ready, when it is convenient, if any uncovered area is there, you can plan for a chill or extending a pad or additional risers. Calculate the pouring weight, pouring time and choke area. Calculate the gating elements. Do simulation if facility available and fine tune the results. So step by step we'll go by doing this methoding. Study the drawing and mark junctions, heavy section need feeding. The science of casting modulus calculation is based on the subdivision of complex parts into simple basic components as shown in the sketch below. I will show you an example. It must be borne in mind that the subdivision is only imaginary. The imaginary interface between two basic components is certainly not a cooling surface. Subdivide the casting into basic shape which need feeding and use simulation software if available. Let us do this following example. So I am taking a small example for understanding the calculations. So this is a 3-inch ball valve body. We have marked up flange 1 F1 and F2 for the second flange, ball side flange and seat ring area and the gland area. There are 6 sections we marked. So part is divided and numbered based on section need feeding. Here the pad, it is available in the drawing itself on the still number 4. So that is helping to feed the seat area from the gland section thickness. So this is the design of the best design of the valve company. It helps the foundry person. There are some items there is no pad. Calculate the modulus of the selected section junction. Find the riser diameter. Modulus equal to volume is cooling surface area, which is shown here in the example. And you should not take the drawing thickness, and it should be the inscribed circle where the junction is there, considering the fillet effect. The modulus should be 72 into 115.
Not viewing, sir. Excuse me, sir.
Yes.
Drawing not viewing.
Not able to see?
Yeah. I'm watching you only.
Sir, we are able to see, sir. We are able to see. We are getting the screen. Please check your settings.
So I am only on the screen is being displayed.
I think maybe some setting issue, sir. Sir, request to check at your end. I think we are able to see. Yes, sir. Please go ahead, sir.
Okay, thank you. Consider the draft and machining allowance from the actual pattern dimension. Do not follow the drawing dimension. With 3D modulus can be an individual feeding region and weight can be easily calculated if 3D model is available. Nowadays, everybody is doing CNC pattern, so it is easy for the engineers to find the modulus and weight of the sections. That is very easy nowadays. If code holes are present, apply suitable correction factor. Wherever possible, or record draw full scale view of the particular section and do calculation. Do not assume. Or use the 3D model. We need not to calculate the entire casting volume and surface area. Consider only location, area to be fed and modulus of the selected section. Riser attached particular modulus of very stick. Refer the sketches. Okay. So these are the basic formulas which can be used for calculating the modulus. Different sections. These are basic you can use and find the modulus. Feeder should solidify later than casting, that is M riser should be greater than the modulus of the casting. The factor 1T is required to compensate for the additional cooling surface area which is generated as the riser continually feed metal the solidifying casting. For steel casting, multiply the modulus in mm with 6.4 and sand riser and 4.3 to 5 depending upon the sleeve efficiency which you have arrived in your foundry for the exothermic sleeves. Follow the standard table provided by the sleeve supplier and do not use other supplier sleeve standard with the other one and get confused. And foundry should make their own standard correction factor based on the sleeve manufacturer recommendations and do a cube test and confirm the sleeve efficiency on factor of safety. So we go as per the drawing F1, F2, F3, F4, all the sections. We enter the dimensions and we find the mean diameter, casting thickness, and plan the circumference, cross section area, and now the modulus, the non-cooling area. Drill number 8. Lance correction perimeter. This one modulus equal to serial number 8. C9 by C10 11.1. So riser diameter considered is 49.7. We are rounding up to 50. Like that, in every section, the modulus is calculated, riser is arrived. This is available in the Excel file. I can share if anybody wants. Calculate the feeding range, feeding length, and feeding distance. So we see in the plant, as for the plant, it is already we are given circumference, that is the feeding distance supposed to be fed, and the thickness of the flange is 30 mm. So for the plant thickness, the feeding length, feeding distance is 4 times the thickness. So from the riser side, both the side, calculate the feeding distance obtained in parallel section where components are increased by bishop, widen the plates and bar casting. This data can be used to determine that data is shown here. So you can use these sketches to find the feeding distance and use the feeding distance formula. Calculate the number of risers, adding the diameter of the riser and the 4T or 5T with the chill or without chill, whatever is shown, what you are applying, whether it's a plate or bar, and find out the feeding distance for a particular riser on the section thickness. So a number of risers is find out from dividing the feeding length divided by feeding distance. For aviary castings, mark all the feeding region, ensure the entire casting covered with the feeding and chills. And wherever number of risers coming, then you have to plan for cut-off chills or action, use the chills where the feeding region is not covered. You can follow like this. This is the example given in the whatever. So without chills, the number of risers are more. When you use the chills, the number of risers are reduced and it is improving the yield. So feeding distance can be increased by adding padding or chills. The padding methods it will be shown in the last sketch. And decide whether it is a side riser or top riser. If it is side riser, then you have to calculate for the neck contact modulus, that is should be 1.1 the modulus of casting. The side riser should, then it will have a foot up to keep the riser. Then the foot up weight also to be considered along with the casting weight for the riser to feed. So here flange circumference is 458, feeding distance of the riser is 240, that is 4 times into thickness. Number of risers required 1.5, so round it up to 2. So like that, all the 5 sections we arrive at the risers. Neck contact dimension for side riser, we already told it should be, neck should be 1:1.1. So calculate the neck riser, that should be equivalent to OD, and thickness of the cast. This can be 0.6 to 0.7. Cross check the neck modulus and ensure that it is meeting 1.1. Otherwise, adjust the dimension width or thickness depending upon the section you are going to connect. Because sometimes the width may not connect, then you may have to increase the thickness. And also sometimes top and bottom risers are coming, then you have to 3 riser, then put up should go fully in the bottom. So then all the neck should be in the bottom. You have to decide accordingly, depending upon the number of risers and position of the riser which you are going to use. Neck to be, the put-up radius to be spherical radius. See, normally I see in foundries not keeping the spherical radius for the bottom side of the put-up. So it is better so that it will have a better surface area and improve the yield. And also should have a well base. This is also not followed in many of the foundries. They simply keep a flat base. It is suggested to use a spherical base. Calculate the feed volume for the selected section. Feed volume, we need not calculate the volume. We use the weight from the model. The weight you have to calculate is 1 casting weight for the given particular riser region, that what you have marked the feeding distance and the riser. And along with that, for this example here, the flange and the flow bore, there is a 10 mm wall thickness area that will also get self-feeding from the flange. The adjoining area up to the 4T or 5T and the foot of weight. You have to calculate both the foot of weight, the adjoining area weight and the job weight. Using this weight, calculate the volumetric shrinkage to be fed from the riser for the selected area. So the volumetric shrinkage varies depending upon the alloys which you are going to cast. So these are some of the examples given. So carbon steel 67% and heat resistant steel, and with different chemistry and cast and azane. Even though they say cast and azane expansion, but heavier sections we have to consider risers. Calculate the riser height based on feed metal requirement. We arrived already the riser diameter and what the weight we need we know. So we have to find out the height from the weight what we need from the riser. So the riser efficiency should be considered. For that the riser, what is the riser metal you are using, either sand casting or insulating riser or exothermic riser. So its efficiency are given by the suppliers. So take care of that efficiency and calculate the riser weight you want. Foundry should make trial and make their own standards to confirm the efficiency. Calculate the riser weight and height as explained in the given example. So we will see the next calculation. The weight of the riser is 7.6 kgs. At the 6% for steel casting, it is 4.45 kg the feed metal. So it will vary depending upon the section thickness. Calculate the riser weight and height as explained below. So weight of the riser for 25 mm I taken as a guideline so that I can arrive the height. So weight what we want to feed is 5.9 kgs. For that, volumetric shrinkage as per 6%. Weight of the casting to feed per riser is 3.8 kgs. Since number of risers 2, we need to add side riser, then consider the weight of the riser foot up. And that is 0.9. Total weight to be fed by one riser is 4.6 kgs. So feed metal required at the rate of 7% for this 4.6 is 0.33 kgs. So the efficiency of the riser considered as 40%. So then weight of the riser should be 0.96 kgs. So this divide this by the 25 mm height of the riser weight. So we will get the riser height. This is 2 inch. So 2 inch is sufficient, but we have the job height. The job height above the per line is 180 mm, and with the foot up, it is coming 72 mm. So you can go for 3 inch, but above the flange you have to keep for the safety for the liquid contraction. So we are keeping 50 by 100 mm. So this is the riser height we arrived now. So repeat the steps for all the other areas like this. Weight for all risers, add casting and foot of weight and find feed metal requirement. Warping sternum here will get feed from flange 1, like that other areas will get from the other flange. The rectangle flange will feed the seat area one side. The mold of the seat area is less than seal area, so it will get feed from the top gland area. Calculate the pouring weight, pouring time, and gating ratios and gating element dimensions. So follow the gating ratios depending upon your experience on the metal being cast. So steel foundries we normally use unpressurized. I've seen some foundries use also pressurized gating for some items. So pressurized different ratios followed for pressurized gating and unpressurized gating are given. Considering the riser diameter and height, riser weight is 7 kg, riser foot of weight is 4.5 kg. Assume down through gating system, and pouring casting weight is 25 kg. So now the pouring weight is 38.5 kg. And from this, find the pouring time. Pouring time is the square root of pouring weight using. And from this pouring time, you find the choke area, that is square root of pouring weight by 1.1 times the pouring time. That is coming 30.6 mm diameter. That is the choke, that is the down screw diameter, because in steel casting, down screw area should be 30 dia. Then with the using the ratio 1:2 is 1.5, calculate the runner size, that is given here area, and in-gate area is given. Calculate the theoretical yield, casting weight divided by pouring weight. After actual casting, record the actual casting and pouring weight in the sample root card. Now you can decide the parting line and the process. Plan for additional requirements of mold box, riser sleeves, padding, material lifting and clamping arrangements, pattern, mold card, everything. And process parameters like seals, profile seals, core hollow making piece, templates, and fixers for core assembly, etc. This is part of pattern design, but after designing the gating only, then we know what are the things is required. So this is my way of suggestion. So if you can use that. When the pattern is received, made ready, arrange inspection and match plating if required to require loose gating and lifting arrangements for pattern. Computer aided. If software is available, run the simulation and confirm the result or fine tune before sampling. Sample casting. Make a method sketch. Write all information like size, type, and number of risers. Mold and core process, box size, special inspections. Instruction to include method card and pattern or core box or marking hollow in cores. Use of dummy or making hollow in cores. So especially this is important in steel castings to avoid any crack. And marking up, cutting in the mold brackets, cooling brackets to avoid cracks. Use of templates for core joining, core pasting, that two halves are joined always in steel foundries. So you make a gauges for that. And some areas we use a zircon or chromate sand to avoid fusion and to avoid in between seals to avoid cracks and avoid fusion. We will put it in the fillet areas. All that you have to mark in the method card and also on the pattern or core box wherever it is required. And chills, for chills we can fix a location and write the chill size, type of chill, riser type chills, quantities, all that. And keep vents wherever not there is no open riser or expected areas where they are locked. Make all marking as per method card on pattern and core box. Verify with the method card on the marking so that nothing is missed as per the planning.
In the 3 legs.
Pattern. Then while making the sample mold and closing, please observe all the steps. Making the mold and core setting and closing, clamping and weight placement, everything should be observed by the development person, so that he knows every step is missed or something is happened that going to affect the quality of the casting. We can correlate after that seeing the knockload casting. Mold core wall thickness, parting line mismatch, mold bend, gap between cope and rack. Some pundits keep video photo also they are keeping for sample making and closing. So during pouring, record the temperature, pouring time, temperature in the furnace, temperature in the ladle, and lighting up the gases and providing the anti-piping. But anti-piping compound, people are not simply putting some bounty, but as per the supplier, you have to weigh and keep the packets and put it properly, not just simply putting by your spoon. So this one point is missing in many of the foundries which I visited. And pouring time, it's an important thing, whether as per the calculated pouring time, did it been poured or not, if any difficulty in that or any disturbance while pouring, all that the person should record, so that based on the casting result, we can correlate the reason for the defects. First, in front of short blasting, you have to inspect and any difficulties in cutting and visual defects. And also the person should involve in the dimension inspection and see that the person is following the drawing reference and is taking the pattern reference, not on the ground area or mismatch casting. All that this inspection also, this is part of the development person should observe. And observing the NDT results, especially in RT, before you are sending in the casting for radiography, you should make the casting thoroughly inspected. Any visual repair should be repaired and take a note of the defects, and then send the casting for RT. Sometimes what happens, people for urgency send the casting without seeing. Then this visual defects seen on the RT, then they are unnecessarily repairing and taking action for that without knowing this is the visual defect. And the method person should aware of NDT reading, how to interpret the film. So many of the times what happened, the NDT person gives a report for the gas or shrinkage as a crack or a gas or shrinkage. So and shooting sketch also you have to be careful and see how he is shooting the casting. RT film view should be evaluated, whether it is any expansion of the view or contraction of the view compared to the casting size, so which will change the level of the defect. Method change, keep record of old casting dimensions, machining allowance, defect location, nature and percentage of defect before proceeding for method change. Sometimes reverse method is a new problem. So without seeing the actual effect, we simply change something, then we invite some other problem because of revision. Sometimes we have to change the top and bottom totally together. So that time this will help. And as per Scrata, some points I want to share here. What they suggest, it should be faster or shorter pouring time. In many foundries, the pouring time is not as per what I suggest, square root of pouring weight or less than that, but it is more than that. So in that case, then we are having a lot of defects. So Scrata is suggesting use a faster pouring, and to achieve the faster pouring and meet the pouring time, our down screw and the nozzle should be matched. The down screw dia should be 1.2 times of the nozzle diameter. So first we are deciding down screw, that is our screw diameter or the choke diameter. Based on that, the nozzle should be selected in the ladle in case of bottom pouring ladle. And throttling should be completely eliminated if the nozzle diameter and down screw is matched like this. Ingot in bottom and top runner, both are working. The pouring time, what they are suggesting is square root of pouring weight into M. So the same thing is which I am following. And if you are pouring fast, this inclusion things can be avoided and erosion can be avoided. That's what they are saying. Inclusion also arises from breakdown of mold. That is, degree of erosion which is likely to occur in a mold system is less when the mold is poured quickly. Faster pouring also allows pouring temperature to be reduced so that you can reduce the cost and reduce the defects related to high pouring temperature. More consistent pouring time, which should result in a general improvement in as-cast quality. Pouring rate can be achieved by simply eliminating throttling by the ladle operator. Nowadays, the quality of the casting is in the hands of the ladle man who is throttling the casting. So to avoid the throttling by the person, then we have to design our nozzle and downthrough properly. And ingate in the top and bottom are working. Preferably, the ingate should be in the bottom and runner in the top. So that is giving effect simply effectively by placing the ingate on top of the runner for gating system. This is the padding method where you have a junctions and keep a riser. You can add a pad using this infrared circle and keep the pad wherever you are going to use top risers. And this is the sum of the defects due to premature neck modulus, that is solidification of the neck. So that is why you are saying that neck modulus should be 1.1. And sometimes we assume this is a pinhole porosity, but it is a centralization case. And in some of the castings, due to sharp cores and very close, the flank to riser is creating a gas problem that should be taken care and should not be misguided with the defects. And always avoid sharp corners, sharp edges in the pattern core or in the in between riser and flank section. So is there any questions up to this? So I can go for any risering and gating principles.
So I think we can have it a question and answer session at the end of the session, sir.
Yes, we can go for gating system, the different gating systems. So you know everything. This I'm not going to elaborate. Gating for ratio we are the same. I think we will not elaborate all this. If people want all this gating fundamentals, all are experienced persons. So the functions of gating is should produce laminar flow and minimize the turbulence. So turbulence will create other defects. So it should be a laminar flow. For that, we are using the non-pressed gating system in steel foundries. Elements of gating, you know, under extension, screw base, pouring basin is required for all the bigger castings, and vents, all bigger castings and core prints where there is no open riser. And for heavier castings, you have to go for ladle, bottom pouring ladle. For that, we discussed the diameter of the chilling methods. When we are using chills, there should be air gap, and that will have a lesser effect. How to keep chills, what are like this one, and the effect of chills also you can see. Chills are used to create end effect, create cutoff effect in between two risers, and establish a artificial end effect, increase feeding distance, promote directional solidification, and avoid hard tears, internal sealing of junctions, and partially improve yield. Types of seals we use: external seals, internal seals, and based on that, top or cope seal, drag seal, profile seals, rod seals, like that. The thickness of the seals should be 0.5 to 1 time, that is thickness of the casting. As per Lodite, 0.66 is effectively working. And the width of the seal should be T2 2 times, and length can be up to 3 to 4 then, or depending upon the feeding distance what you are looking for. People use up to half of the profile also. And the use of seals is important. Prepare the seals properly, ground, coat with a seal coat, and use a correct seal based on the section thickness and the type of seal given in the method card. Do not use the chill, just the namesake, because we always see some people make wrong chills and fused with the casting or problem of in the bulk castings. So chill management is important in the foundries. So this is properties of chills, how the cooling effect they give different, but we still foundries use steel slab chills. So chill work 4 times less casting thickness. And somewhere we are using shots or chromate sand, zircon sand. Their effect is given here. You can make use of this. So the defect related chills are, if the chill is not properly ground or coated, then you will have this gas defect below the chills. Always that is a problem in chill foundries. And if you are keeping over more number of chills, then there is a chance of crack around the chills. So then you have to distribute the chill and keep a proper sand thickness in between chills and proper thickness. So inside chills where you will get a crack, they given some example and go through it. And the defect due to adjoining chills or tears. And some case we are using fins. So these fins will work in place of chills, but we normally use for avoid cracks cutting by way of cutting brackets in steel castings. The risers, anyway, risers we have discussed. So why we use the risers? Found if the metal is melted and poured at high temperature, solidification of liquid temperature plus superheat to increase the fluidity. With the pouring metal solidify the cool to form a casting. They generally undergo following 3 distinct stages of volume contraction. That is, one is liquid shrinkage, that is taken care of riser height, extra height, and the solidification shrinkage, that is liquid to solid contraction. For this, we are keeping the risers. So that's why we have discussed so far how to calculate the riser. And the solid contraction, that is taken care of by our shrinkage elements in the patterns. Subsidiaries have adequate volume to ensure availability of feed metal to all the section, satisfy molding constraint and thermal adequacy, economy of the casting, that will have a higher yield. And it should promote directional solidification. The riser casting junction should be designed to minimize the riser removal cost. And type of riser based on the placement, it is top, side, or core riser, open and blind riser. Based on riser material, sand, insulating or exothermic or insulating or exothermic. And based on the shape, it's a spherical or cylinder or elliptical shape. And there are shared riser, that is a common riser for 2 junction sections or 2 castings. So I think with this I conclude. If anything, any questions we can ask. Hello.
Gentlemen.
Hello. Yes, sir.
So are you able to hear me?
Yes.
Gentlemen, I think the speaker has completed his presentation. If you have any queries, we would request you to raise it now. Sir, I think there are some questions arrived in the chat.
Yeah. Okay.
One Mr. Ravi Shankar, I'm reading out. One Mr. Ravi Shankar has raised it. What is the advantage and disadvantage of in-gate connection? That is at bottom cavity, at parting line, nearer to middle height range of cavity, and third at the top side in SG casting in-gate design.
Okay. That is like a step in-gate. It's asking. The bottom in-gate, it is always advisable, but making a bottom gating, especially in SG iron, is difficult. unless you use a refractory gating. Parting line gating is always we are using. In that I explained whether you can use a in-gate in the top or in the bottom of the runner. So using at the parting line runner, in-gate and runner over the in-gate is a preferable station as per my experience. And top in-gate connecting to the riser is best to feed the riser with the hot metal. It is possible for you to keep such a gating system is good. That's depending upon the casting nature or your process. If you are using a vertical parting and cake mold, then all this is possible.
Any other questions?
Sir, good afternoon.
Good afternoon,
sir. Please introduce yourself, sir.
Yes, sir. My name is Bapu Nara Nirmale. I'm from Kolhapur.
Okay.
Okay, and we have one question regarding the insulating and exothermic sleeves. Okay.
Yes.
How to use both the sleeves for the steel casting? Okay. Generally, in insulating,
depending upon your casting, you are deciding the size of the riser. So now we have discussed how to calculate the riser size. See, actually, the sleeve suppliers are supplying more than 6 inch are coming only in the insulating sleeves. They are not exothermic. The exothermic risers have a more efficiency. It is explained in the table, that is 40 to 50%. The insulating sleeves have a lesser efficiency, that is feed metal. So you may need a bigger riser when you are using a insulating riser. So if you use the exothermic riser, then you will get a better yield.
Sir, generally in insulating sleeves, we are getting 1.4 to 1.5 MEM. Okay.
Yeah.
And in exothermic, generally, as per the supplier specification, it is coming 1.6 to 1.7 MEM. Okay.
Okay. But practically, I will check. You have to confirm from your side.
That is okay, sir.
Based on your molding practice and pouring practice.
Checking in the cube and checking in the casting, that is about the difference.
Okay.
So if it is showing a 20% safety margin with 1.6 MEF in the cube, shall we reflect in the same casting, same result in the casting?
Yes, correct. Provided that cube test is okay.
Okay.
Yes.
So what is the general feed efficiency for the insulating and exothermic sleeve for the casting? Low alloy steel, you can take it.
That's what, sir. Less than 6 inch, you can use a exothermic sleeve so that you will have a better feed metal, so that you can, that is a 1.6, that means it gives you 60% efficiency. From a 10 kg riser, you will get a 6 kg as a feed metal. If it is a insulating riser, then you will get only 4 kg riser feed metal. So you are saving 2 kg, no? And the cost also you have to calculate, and economics you have to work out. Anyway, it is above 6 inch, it is only insulating.
Sir, what we are doing, going with modulus or feed metal requirement, take as a low alloy steel. It is feeding efficiency, feed metal requirement is 6%. Okay. So suppose it is 100 kg casting, we can take as a 6 kg. Okay.
Yes.
So if it is going with the sand casting, considering 10% efficiency for the safety purpose for the process variation. Okay. It is coming 60 kg of sand riser, correct?
Okay.
So what we are doing, to that 60 kg sand riser, we are dividing by the 1.6 or 1.4, whatever the MEF specified by the supplier.
You don't go by the MEF. See, you are now we have explained you how to do the modulus. Do the modulus, find out the riser size for the exothermic sleeve. Okay, then from there you find out what is the feed metal required. We given the riser height, how to calculate the riser height and feed metal. You use these formulas and you will get. So if when you are going to use a insulating sleeve, then you use that 40% efficiency. When you are going to use exothermic sleeve, use the 60% efficiency. Then you will get the correct
knowledge. As per our knowledge, exothermic sleeve will not give 60% feeding efficiency.
Yes, practically it is not giving. That's what I mentioned. You should make your own standard and confirm with the cube test.
Yes. As per our knowledge, and a lot of people are here also from the methoding. It is an exothermic sleeve giving feeding capacity not more than 35 to 40%.
Okay. Sir, it is working up to 40-45%. It is giving branded sleeve.
Yes, sir. You can take as a branded in the market. it is not more than 35 to 40%. If there are a lot of people are there.
Use your practical experience. Don't go by
Yes,
the
sir.
supplier.
Because I was the executive for the selling this product. Okay. So, and including we are looking at the 25 to max 25%, 30%. You can say their experience also in this.
Hello.
Hello.
Sir. Yes, sir. Your voice is not clear, sir. At the end.
Okay. Whatever I told now, exothermic sleeve 35% and insulating sleeve 20%. Other guests are also there. They can share their view.
At least I am not getting it. I don't know whether speaker is able to.
Sir, that's I explained you. See, the exothermic sleeve will give a 45%. That means it gives 4.5 kg of feed metal from this weight, 10 kg riser. Okay. Insulating sleeve gives only 3.5 kg from the riser, 10 kg sleeve. So then you have to consider that sleeve and the riser size, diameter or height accordingly. That you have to arrive at from your own cube test result and apply to them.
Okay.
Don't go up as per the supplier recommendation. It is not practically meeting many of the cases.
Yes.
Even in simulation, we are failing. If you are playing the same thing, so we should be careful in judicially using the riser size and volume.
We can cross-check modulus as well as the feed metal requirement, sir.
Yes. From the modulus, you can find out the riser size and the casting weight where the riser is going to feed. That weight you have to take and find out its feed metal requirement, how many kg it is required. From there, divide the riser efficiency 30%, 40%. Then you will get the riser weight. Then find out the riser height.
Yeah, so we can cross-check with feed metal requirement as well as the modulus.
That is important. Yes.
Yes.
Not just by seeing the riser size or riser diameter, it's not going to help.
And
sometimes the modulus is giving is 6 inch diameter, but we are forced to use 7 inch next size riser to meet the feed metal requirement. Say for example, casting need 5 kg feed metal. Then my riser is coming 3 inch. So 3 inch weight comes only 5.4 kg, but I want 7 kg. So then I have to go either 3 by 8 or if it is more than 7 inch, it is not recommended. So go for the next size riser. Instead of 3.5, go for a 4 inch riser.
Yes.
So that is the important thing. And if you can able to reduce that by using shields, put a shield and see whether it is compensating that small shortages.
One more question I have.
Yes,
okay.
Please.
Going with 1:1 riser diameter height is good or 1.5 or 1.1?
The 1.5 to 2 is always better. More than 2 is not going to help you. But for smaller castings where the thinner casting, you can even 0.5 times the diameter is also working height where there is so much feed metal required, but riser is required especially in SR heat resistant steel castings. For the junctions, we can keep smaller height also. In case of exothermic, not sand riser.
People are using 1:1 riser ratio and they are getting
the debate ಮಾಡ್ಲಿಕ್ಕೆ grapple ಮಾಡ್ತಾರೆ.
Hello. Sir, any question? Your voice is not clear.
Yes, sir. I have a doubt that people are going 1:1 riser diameter ratio and they are getting very good result. What do you recommend, sir?
What, sir? Repeat.
Lot of people are going. Hello. Hello.
Sir, yes, sir. Your voice is breaking, sir. Can you put this content in the chat, please?
1 minute. chat
Sir,
मध्ये.
meanwhile, go for other question which has come in the chat box.
Okay, no
Sir,
problem. No
one
problem.
Mr. Dinesh Babu is asked question how to calculate pouring time.
Yeah,
So there is a question
tell me.
in the chat box.
Hmm.
Mr. Dinesh Babu has asked how to calculate pouring time.
Pouring time, it is there coming in the presentation, that is square root of pouring weight into the constant that varies from molding process 0.67 to 0.885, that is even 0.9. The format is there in the calculation. That is the formula which I am using and practicing it.
Okay. So it is mentioned in the presentation. I think if
Yes.
you are not noticed, it will be uploaded on the YouTube. You can see it at the later time, sir.
Yes.
Okay, sir. The next question from one Mr. Pondraj. How to select the chill material for which type of casting and which and the chill dimensions?
Dimensions I explained just now. That is depending upon the material. Say steel casting, you have to use better steel casting. For iron material, use iron chills. For non-ferrous, if possible, you can use cast iron chills or copper chills. And chill thickness is 0.5 to 1 times the thickness where you are going to feed. And width and thickness length should be based on your feeding requirement length. If required, you can use 1 time the thickness or 2 times, up to 3 times you can go for the length. That is also I shown in the chill section. If you want, I can elaborate. I'll show it again. Okay, then next.
So you are sharing your screen?
Hello. Now for side racer, if you are having shingle, then you check first whether feed metal is there and your neck modulus is meeting 1.1. Two things you have to check. If there is neck modulus is okay, then feed metal requirement for the particular section is okay or not, you check. Maybe your neck modulus is not meeting. And riser boiling, maybe sleeve you are not kept it properly stored with the plastic cover, moisture, maybe due to this rainy season it may get wet, or due to paint it will get wet, then it will chances of boiling. Or sometimes if any thin core inside get break, then due to gas it may boil.
So the next one is someone has, okay, they are asking us to send a PPT and paper. Okay, sir, this will be uploaded in the YouTube. You will be able to see that later stage. Sir, next one is from MSPL. Sir, how to select BOB size, slag collection and hot well size?
Slag collector then? The other one?
Slag collector and hot well size. Hot well, sir. Hot well size.
Hot well. That is screw base. Okay. That I'll show you in the getting system. That it comes in cast iron and SG and not in steel boundaries. We used to keep that choke, pressurized getting system. There the choke will control the slag in the runner. The screw base is the screw diameter into 1.5 times dia and 2 times the depth. That is the normal standard. Sometimes some people use the same 1.5 to 1.5 also. And for bigger casting, we go for a refractory sleeve base, the tiles to avoid erosion. Smaller castings only we are using screw well. And bigger castings are poured with the refractory sleeves and gating. The shape of feeders based on, see, normally spherical riser is the best, giving best result. It is not practical to make, but we use the spherical riser in case of vertical particle we can use. So that's why we are going for cylindrical risers. Wherever I mentioned in that, if you are one riser not connecting, then you can go for your oval riser. But some people are not happy with the oval riser, oval shape. They always go for a round riser with additional pad. And blind risers is the best way to use. crack depending on the section thickness, and it is not only because of getting, it also plays the metallurgy depending upon the chemistry, and we always put a cooling brackets where the crack is coming, make the core very hollow, prevent the shrink of the core. Next, high efficiency racer. High efficiency racer, I think they are using in end condition in the course where a small feeding is required, boss like that. That we are not using in seed boundaries. Anything is there, the supplier can contact us. We are welcome to use. Cooling bracket size that is less than the modulus of the connecting section. That is 5 to 6 mm, 8 mm is sufficient. That should be more than 3 mm so that it can form properly. And it's preferably if it's a lot of brackets required in our cattle bar components or some other structural castings, we can fix it in the pattern itself. 5 to 6 mm thickness at the space of 3 inches, 4 inches, or 2 inches, depending upon the area where you are having a place. Ingate corners, you can check your radius or ingate thickness. The ingate should be less than the modulus of the connecting section, less than 0.5 T. That cross check and confirm. That is 1:2 is 1.5 is the ratio. What I follow, I get better result. Dinesh. Thank you.
Hello.
Yes, sir.
Sir, a lot of questions are pouring in. I think.
Okay,
Are you able to see the chat? Maybe we will take.
Ratio.
Yeah, we'll take some 1 or 2 questions, sir. Then we'll close it.
Yeah, no problem. Any number of questions, I am ready. See,
Okay.
for choke area, you have to decide first what is your getting system, whether it is a pressurized or non-pressurized. If it is a pressurized, then it will come in the choke. That is down through runner in the ingate. The ingate is going to be the choke. In case of unpressed system, it is the down through diameter. So the down through itself going to choke your this thing. So that is the choke. Okay, sir.
Manohar sir, we will close it because I think there are a lot of questions are coming in. Let's take it on offline. Maybe the time we are also reaching our time limiter. Okay.
Okay, right.
Yeah.
Okay.
Yeah. Hello, Foundryman. I think we indeed had a very fortunate hands-on experience Foundryman who talked us this subject he loves. Thank you, Manohar sir.
Thank you all the participants. Thank you, IIF
and educative presentation on gating and rises for steel castings. And speaker has touched very basic of the subject and gave a lot of formulas. It almost taken us for our college times. We can also witness that sound of topic by the way of various questions from the participants. We are sure that you must have got a lot of takeaways from this webinar. And if you can implement 1 or 2 points in your day-to-day operation, and it defines the success of this webinar. And we would like to thank Mr. Manohar for taking his time off from his busy schedule and for making us rich with knowledge. Further, we would also like to thank all the members who joined us for this talk across the nation. Thank you once again and joining us on time and being such a wonderful audience. We from Chennai chapter is conducting with IIF Southern Region for many such interesting programs, both physically and virtually, and we'll be sharing information on this on time to time to all of you. We also would like to thank. We would like to take this opportunity to inform all of you to IIF Chennai chapter is having a successful YouTube channel, IIF Chennai chapter. we request you to subscribe the channel so that all the contents or whatever are loaded, you can get the knowledge from that YouTube channel. Thank you once again, and looking forward to seeing you also in our upcoming programs. Thank you. Thank you all.
Thank you, sir. Thank you all.
Thank you. Thank you.